let's talk about Kirchhoff's rules. And these are rules, and this is a technique for solving DC circuits with batteries and resistors. And it's a very cool thing. It lets you do things that are solve circuits that are really, really complicated. Before we do that, though, let's review Ohm's Law and talk about how batteries work a little bit. And then we'll talk about voltage man and how voltage man walks around a circuit and measures voltage and so on. And then we're going to talk about a couple of rules that make up Kirchhoff's rules. One of them is called the junction rule and the loop rule. And then we'll work an example problem, and I'll show you how Kirchhoff's rules lets you solve a circuit. So first, let's talk about Ohm's Law. Remember that if I have current running through a resistor, okay, then, and let's say the current is flowing in this direction, so here's I, then we get a voltage drop. And the voltage drop from here, let's call this A, and we'll call this part B. And the voltage there, delta V, from A to B, is going to be negative IR. Right? That's Ohm's Law. It says we're going to get a voltage drop. And so when it drops, I'm going to call it negative IR. Now this really means that we're going from A to B. But what if I want to go from B to A, right? I'm going to go, instead of going from A to B, like all this is at a high voltage and we drop this much voltage. But what if I want to know what is the voltage difference between B to A? B to A. Well, now, if I'm going in this direction, whoop, I jump up in voltage. Because what a resistor does is it drops your voltage as current flows through it. But if you're walking through the circuit in the opposite direction as the current, you actually jump up a little bit. So that's going to be positive IR. Okay, so that's this is Ohm's Law, and we're going to be using Ohm's Law to, walking around circuits and figuring out what the voltage drops are based on the resistance and the current in the circuit. And then let's talk about batteries. So let's say here's our negative side and something like this. And we're going to go from A to B. Now, if I'm traveling along like this, here's the EMF of the battery, and maybe there's an internal resistance, maybe there isn't, depends on the problem, probably won't be. But if I go from A to B, if I the voltage change, if I'm going from A to B, if I go from here to here, whoop, okay, it's a jump in voltage. So all the stuff on this side is at a higher voltage than the stuff on this side. Okay, so that's going to be from A to B, it's going to be just equal to E. But what if I change direction? Oops, sorry. What if I go from B to A? Now it kind of looks awkward, but what if here's A and here's B. What if I go this way? Well, think of it this, look at how this is drawn. Do you see how this is higher than this? So you're stepping down in voltage. That's the way to remember it. So this will be negative E. Okay, so what we're going to do today is we're going to be walking around in circuits, jumping across resistors and batteries, and so we need to know whether it's a voltage gain or a voltage drop. Now notice that with a resistor, it depends on the direction of the current, but with a battery, current is irrelevant. All the battery does is says, hey, all the stuff over here has less voltage by this much than all the stuff over here. Okay. Now, if you have a, let's say we have a circuit, and let's take a look at what voltage man does. Okay, so let's take a look at a simple circuit, something like this, and maybe we have a resistor here. We'll call this R1, and then here we have R2 and R3, something like that. Now let's say obviously the current is going to be moving in this direction, right? And then it's going to go down here. Then it's going to split up, and some of it will go this way and some of it will go this way. But remember what voltage man does. Voltage man goes in circles around a circuit or completes a closed path. So voltage man always starts somewhere and then walks around the circuit. And now when I come to a junction, well, this is called a junction, I can either go this way and get back to where I started, or I can go the other way. I can go around like this and go this way and get back to where I started. And what voltage man does is he or she or it makes sure that the voltage increases have to be equal to the voltage drops in order to conserve energy. He is the guardian of the conservation of energy within circuits. So that's a really important superpower. Okay, let's put an EMF right there, and then let's call this I. So now we're going to get to Kirchhoff's rules, and it will allow us to solve circuits that are even more complicated than this one. Let's talk about the junction rule. We already talked about the junction rule. Now, what these rules are going to do, the junction rule and the loop rule, they're going to give us equations that will allow us to solve a circuit. And when I say solve a circuit, I mean we're going to know what every single current is, we're going to know what every single voltage drop is, and we're going to know how much power is going out every single resistor. We're going to know everything about that circuit. Now, one of the things you have to know in advance is, hey, what are the batteries and what are the resistors? But if you know the batteries and the resistors, you can use these rules to figure out what the currents are, what the voltage drops are, and what the power out the resistors are going to be. Okay, junction rule. Okay, a junction is any place where you have a branch in the wire. And all the junction rule says is, hey, the amount of current that comes in has got to be equal to the amount of current that comes out. Otherwise, charge is either building up for some reason, and that's not going to happen in a junction, or you're creating charge out of nothing. So really this is kind of a conservation of charge. However much charge flows in, we'll call this I1, I2, and I3. And then what we can say is we can say, hey, if you add up all the currents going into a junction, it has to be equal to all the currents coming out. Okay. Now, so in this case, here's what I would do. Or actually, hey, when you add up all the currents going in and then you subtract all the currents going out, it equals 0. That's another way of writing this junction rule, right? Okay, so what we're going to say for this junction is I can write an equation. I can say, hey, I1 minus I2 minus I3 equals 0. Now, the trouble with this equation is that there's one equation, but 3 unknowns. So what we're going to do is we're going to need to figure out, we're going to need more equations. And we're going to develop a system of equations, and then we're going to solve for the currents. Okay, so let's talk about the loop rule. This is the second of Kirchhoff's rules. Okay, and basically the loop rule is really the voltage man rule. And it basically says that when you add up all the changes in voltage in a complete loop, if you complete a loop, when you add up all the changes in voltage, when you're going around a circuit, they all have to add up to 0 if it's a closed loop. And voltage man likes closed loops. He likes to, finish what he begins, where he started. So we're looking at here. Here's a closed loop like this. Or, in this circuit, you could even start here. Voltage man could start here and go in a closed loop like this. And what he says is that voltage drops have to be equal to the voltage gains to get back to where you started. So any time, any kind of loop you can form in a circuit will conform to this rule. If you start somewhere and end at the same place in the circuit by doing a complete loop, this will be true. and this is conservation of energy. So really the junction rule is conservation of charge, and the loop rule is really conservation of energy, or energy per unit charge. This is actually charge. The junction rule is charge per unit time, and this is energy per unit charge. But same idea, conservation of charge, conservation of energy. And so what we're going to do now is use these ideas to develop a system of equations that will allow us to solve any circuit. And really the best way to do this is to just do an example. Now let's start off with a really simple example. It's almost trivial, okay, but it still will work. So we'll call this example 1. Now the way I do that, to do this fast, here's what's given. To do this, I just draw a triangle, and then I draw a little zigzaggy thing like this, and I say this is R2 equals 10 ohms. And then I want a battery right here, so I'm just going to erase a little bit. And then I hope you're not doing your notes in pen. Okay, and there's my first, this is the EMF of this battery, we're going to say is 6 volts. And then here's a resistor over here, and we'll say that, we'll call this R1, and this is 8 ohms. Okay, and then, just for the heck of it, we'll put a battery over here, and we'll call this E2, we'll call this E1. This voltage change due to the battery will be 12 volts. So this is what's given. Now, what are we trying to find here? Well, I want to find the current. Well, we don't want to write the word. Let's take shortcuts, okay? Let's say I want to find the current in the circuit. And B, let's find out how much power is delivered to each resistor. Power 1 and power 2. That just refers to the resistor. Okay. Now let's solve this. Okay. Now, really, there's no junction in this circuit. It's a pretty easy example. So there's only one current, and so we're only going to need one equation because there's only one current. And we're going to use voltage man to do it. Now, when you're going, there's only one loop, so we're going to use the loop rule. But you have to be super careful. When voltage man walks around the loop, you have to be super careful to get the sign of, whether it's a voltage gain or a voltage drop. Okay, you got to get it right. So you can start anywhere you want, but I'm just going to start right here at the top, and I'm going to march clockwise around. Now, it'll work if you go counterclockwise. It doesn't matter. Okay, but I'm going to walk this way. Oh, look at this. I'm going to step up in voltage. So that's going to be positive 6 volts. So I'm just going to write it as 6 volts. Now, I'm going to go like this. Now, one of the things, when I get to this resistor, let's assume that my current is in this direction. Let's just assume it's in that direction. By the way, if I'm wrong, if it's actually going the other way, and oh, look, this is 12 volts and this is 6 volts, so it actually is going the other way. It doesn't matter. If you guess wrong on the direction of the current, you're going to get a negative current when you solve for it. And that just means, hey, your current's going the other way. Don't worry about it. So just pick a direction arbitrarily. So I'm going to pick this as my direction. Now, what happens is that when I go through here, the current is going through here. And so as the current goes through the resistor, energy comes out of it. Okay, energy is going to leave. And so it's going to be a voltage drop minus IR1. Okay, and then we're going to come over here, and look, I have to step down minus 12 volts. I'm going against the battery. If I'm going against the battery, here's what this battery does. It says, hey, whatever this voltage is, I'm going to make sure this voltage on this side is 12 volts higher. This will have 12 volts or 12 joules per coulomb more energy than this. Okay, so we're going to step down. Step down by 12 volts, so it's minus 12 volts. And then we go over here. Now I'm going with the current. I'm going with the current. I'm going to say the current's going, if the current's going this way, it's going this way, this way, this way. So I'm going with the current. And when I go with the current, I drop in voltage as I go across the resistor. So this is going to be minus I R2. Of course, I know what R1 and R2 are. And now I'm back where I started, so it has to be equal to 0. So now let's solve for I. Let's see, well, let's see, 6 volts minus 12 volts. This is going to be negative 6 volts, and let's put it on the other side. So that's going to be 6 volts over here. And then on this side, I got negative IR1 minus IR2. So let's multiply both sides by negative, and I distribute the I out, and this becomes R1 plus R2. Now this makes sense that it's R1 plus R2. That's the equivalent resistance, because look, R1 and R2 are actually in series. That is, the current has only one path. It must go through R1 and R2. So R1 and R2 are in series. So you just add them together. So to save a little time, I'll just say, what is R1 plus R2? 8 plus 10 is 18. So this is 18 ohms equals negative 6 volts. And so now you just divide, and we get I is equal to negative 6 volts divided by 18. Now what is an ohm? An ohm is a volt per amp. So this is negative 0.333, I guess 3 significant figures, amps. That's my current. Now what does this negative mean? It means I guessed wrong. The current is not going in this direction. It's actually going in this direction. But that's okay. I can just say, hey, the current is 0.333 counterclockwise in the circuit. And so I have solved part A. So I'll just say, how about instead of the negative, I'll go 0.333 amps counterclockwise. Now, what about part B? Well, if you solve part A, part B is easy. Okay, because P equals I squared R. And so you know what I is. It's 0.333. You know what R is, and I'll just leave it to you to finish this example. So figure out the power. It's just going to be 0.333 squared times 8 ohms, and that's how many watts are coming out here. 0.333 times 10 squared at times 10, and you'll get the same thing there. Okay, that is it for this example. Now let's do a much more challenging example, one that's got all kinds of loops and stuff going on. Okay, now I'll tell you what, before I do that, I do want to go back and I want to go back to this example. Okay, let's go back to this example. Sorry. What if I had gone the other way? What if voltage man had started here and gone this way? Now pay attention, because this is where students make the most mistakes in setting up their equation, their voltage equation. If you are going like this, you are going against the direction of your guessed current. You guessed, you took a wild guess that the current was going to go this way. Well, if you're going to go against the current, well, when you go against the current, resistors actually give you a voltage gain. A voltage gain. So this would be, if I were to rewrite this, let me zoom out a little bit. So if I was going to go this way, I would say, oh wait, this is I, positive IR2. Because you can kind of think of resistors as being like little waterfalls. And the current is the water going down this little waterfall. And the water, as it goes down a waterfall, is releasing energy into the environment. That's what resistors do. They release energy into the environment. Well, think of a salmon swimming against the current of a stream, and it has to jump up in voltage. You're moving against the current. So you're like a little salmon that's going to jump up here to get to a higher level, so that somewhere you can spawn and die. Well, not with a circuit though. Okay, so you start here, and you go and you jump against the current. You gain voltage, then you're going to come over here. Oh, look, I'm going with the battery. I gain voltage. So that's plus 12 volts. And I'm going against this current. I'm still going against the current. So I gain, so that's plus I, R1. And then you go over here. Oh, I'm stepping down 6 volts. So it's minus 6 volts. And now I'm back where I started, equals 0. Well, look at this equation and look at this equation. They're the same equation. All you got to do is multiply this equation by -1 on both sides, and you got this. So it doesn't matter which direction you go. It doesn't matter what direction you guess for the current, and it doesn't matter which direction when you're going around, when you're voltage man and you're going around in a loop. It doesn't matter which direction you choose, as long as you are correctly identifying what's a voltage gain and what's a voltage drop. That's super important. Okay, and I mean, if you're going to make a mistake on these, that's what you're going to do wrong. Okay, let's do example 2 here. Let's take a look at something with multiple loops. We'll just have 2 loops. And again, so this is example 2. Okay, let me zoom in. Wait till the camera stops screwing around. Come on. All right, there you go. Now, where are my resistors? I'm going to put a 4 ohm right here. And then up at the top here, I'm going to put a 14 volt battery. 14 volts. So that's 14 volts. And then I'm going to so this is 10 volts, and this is 6 ohms, and then let's put a 2 ohm right here. Now, what we want to do, this is what's given. Now, what do we want to find? Well, what I want to find is the voltage through each, not the voltage, the current through each branch of this circuit. And we have 3 separate branches. We have this branch, right? All the current has to be the same here. We have this branch, all the current has to be the same here. And we have this, all the current has to be the same here. So the first thing I'm going to do is identify my currents. And so you pick a junction, and it's random. I could have picked this one. I'm going to pick this one. Let's guess, and it doesn't matter. You can just guess whatever you want. I'm going to call this branch 1, so this is I1. I'm going to call this branch 2, so this is I2. I'm going to call this branch 3, so this is I3. So I want an equation. What I'm going to do is the first equation I'm going to pick. So, well, actually I1, I2, and I3. That's what I want to find. Okay, so now let's solve it. Now the first thing I want to do is use the junction rule. Current in, current out. So the current in minus the current out has got to be equal to 0. So current in, I1. Current in, I2. Now current out, I'm going to give that a so minus the current out equals, now I'm going to leave a space here. Hold on a second. I'm going to leave a space here. So you'll see why here in a minute. Equals 0. Okay. Now, I've got 3 unknowns, so I'm going to need 3 equations. Well, what I'm going to do is I'm going to pick a loop. And so what I'm going to do is I'm going to make this my first loop. I'm going to pick this as a loop right here. It doesn't matter which loop you pick, okay? You just go with it, all right? Now, I'm going to start here, and I'm going to go around here. And voltage band goes, let's start right here, and I'm going to go clockwise. I'm going to go, 10 volts. It's a jump. I'm going up 10 volts, so I'm going to put plus 10 volts. That's what the space is for over here. And then I go over here. Oh, here's I1. I'm going with the current. So I'm going to tumble down the little waterfall. Minus 6I1. That's the voltage drop, right? Ohm's Law. Delta V equals IR. Now, this is the one time I don't show units because I don't want to clutter up this equation. Then I'm going to go down this way. I'm going with the current. With the current. Jump down. Minus 2I3. And now I'm back where I started. Equals 0. And now I need to pick another loop. So let's pick this loop, E, F, C. Let's pick this top loop. Now, you could have picked the outside loop, and that would have worked fine. You got 3 unknowns, you need 3 equations. So I'm going to start here, and I'm going to go up this way. Now look. Let's extend this way. I'm going with the current. I'm going with I2. So this is going to be a voltage drop because I'm going with the current. So this is going to be minus 4I2. And then I get here. Oh, I'm jumping down. Minus 14 volts. And then I'm going to come down here. I'm going with the current, going with the current. Oh, going against the current. I'm going against the current. I'm a salmon swimming upstream. Whoop. Okay, that's a voltage gain. That's going to be 6I1. So here's my I1 column. And then I get here. Oh, I'm going to drop 10 volts. So that's minus 10 volts. Now this is kind of sloppy. So let's rewrite it and combine stuff. And I'm going to put all the I1 stuff in one column. Okay, let me zoom out a little bit because this takes a lot of room. So I've got I1 plus I2 minus I3 equals 0. And I've got this one. I got minus 6I1 minus, oh wait. Now how much I2 do I have in this equation? I don't have any I2. There is no I2 current. The second branch was not in that loop. So it's just 0, or you can just leave it blank. Minus 2I3 plus 10 equals 0. Now look at this one. 6I1 minus 4I2. There's no I3, but look, I got minus 10, minus 14. That's minus 24 volts equals 0. Now I've got 3 equations and 3 unknowns. Now if you want to do it by hand, you can. Some of you with your fancy pants calculators can do this. You're going to get an instruction sheet on how to solve a system of equations with this. You can set up a matrix. I'm going to let you guys figure out how to do that. But what I want you to see is this. What's missing from this one? Here's how I do this. I go, what's missing from the third one? There's no I3. So let's eliminate I3 by using these 2 equations. So what I do is I say, okay, I'm going to multiply this first equation by 2. So I get 2I1 plus 2I2 minus 2I3 equals 0. And then I have minus 6I1 with no I2 minus 2i3. That's the second equation. Oh, plus 10 equals 0. Now what I'm going to do, I want to get rid of I3. And I'm going to get rid of I3 by subtracting these. And you got to be really careful. So what's 2 minus negative 6? Well, it's 8. And then this is just plus 2i2. Now what's negative 2i3 minus negative 2i3? It's 0. And then we have no voltage here, minus 10. That's going to be minus 10 volts equals 0. But now I've got an equation with the same two unknowns as this one has. And I go, okay, what's the easiest thing to do? Let's multiply this one by 2. And then we'll add these two equations together. So let's do that. Let's rewrite it. And this is kind of cumbersome, but you just have to figure out how to do it. 6i1 minus 4i2 minus 24 volts equals 0. Now take this equation here and multiply it by 2. And when I do that, I get 16i1 plus 4i2 minus 20 volts. Did I do that right? Multiplied it by 2? Yes. Now I'm going to add these together. So 6 plus that's 22 I1. This is 0. And then when I add these together, I get negative 44 volts equals 0. No, there's only one I1. I mean, there's only one unknown. It's I1. I can do this. So put this on the other side. I got 22 I1 equals 44. And look at this. I1 equals, well, 44 divided by 22 is 2 amps. Now we put the units back in. And voila, there's I2. Well, if I've got I2, it's pretty easy to figure out what I1 is. Just plug it in here. So let's do that up here. I have 8 I1 plus 2 times 2 is 4 plus 4 minus 10 equals 0. So now I can solve for I1. So I'm going to put 4 minus 10, that's negative 6. Take it to the other side. So 8 I1. Am I doing this right? Am I doing this right? I think so. And so this is what 4 minus 10 is negative 6. Add it to the other side is 6. So I1 is going to be equal to 6 divided by 8. Now 6 divided by 8 is, and I think I have the wrong answer. Oh no. No, I2 is 2 amps. No, I1 is 2 amps. And I can't edit these videos. Somewhere I've made a mistake in here. Let's see, because what did I do wrong? Okay, now I made some kind of arithmetic mistake in here. I bet you can find it. I think I set up my loops right. Did I do this? And by the way, I don't have time to redo this. But you solve it. No. Okay, here's what I'm going to do. Look for my mistakes. I might have made like one little sign error in here. So look for it. See if you can find it. And but I got to go to my class. I'm going to a class. So I have 1 and 1, negative 1. These are the coefficients here. And then this is negative 6, 0, negative 2. And then put this on the other side. Negative 10. And then here you have 6, 4, 0. And then over here, you put this on the other side, you got 24. Somewhere I made a mistake in these loops. You guys got to figure out, this is on That's this one in your book. That's what I was trying to do, and I wasn't following the book exactly. So figure it out. Go through it, figure it out. But this is what you're supposed to do. Good luck.